Okay, so since the designated announcer has disappeared, I have the pleasure of introducing Christian Ikenmeyer for the second part of his lecture, writing down polynomials via representation theory.
Thank you very much. So this last time was about representation theory, and we will now connect this to polynomials and how to write these polynomials down. So remember, we had the symmetric group acting a lot. Was the symmetric group on the letters? So we have a right action, and when we've seen these things a lot, I think, during the last few days. So we have a right action of the symmetric group on D letters, and now I want to have the tensor power. It should be the dth tensor power of some vector space, and I want to call it W star. And it has a star because I want to think of these vector spaces as having row vectors. And how does it work? It's just, I want to have a right action because it's just nicer to have a right action. So it's so I write pi here, and this is a circle, which is my action symbol here, and it will also mean other things. We will use this circle for all kinds of things. So on this, works nicely as this. Of the symmetric group, yes. So that's our right action. And there's an invariant subspace that we are interested in, which are the polynomials, basically. And I want to talk about that for a second. There's an invariant subspace. It's called SIMD W star, which is the set of invariants. It's the subspace of invariants. So, and the point of this subspace is, in our case, that this is actually these are actually polynomials. So you have those symmetric tensors here. So those symmetric tensors are actually polynomials. So if you have an f in SIMD W star, then this corresponds to a homogeneous polynomial of degree d in dim W star variables. And how does it work? So say you have your f, and you want to evaluate it at some, say, v, or say, let me call it h, sorry, let me call it h. Evaluate it at some h, then how is it defined? You can define polynomial evaluation now, which is just saying you have your tensor, it's a row tensor, and you do tensor contraction with a dth tensor power of h. So this is now tensor contraction, right? So this is just basically this is a row vector, this is a column vector, it's just contraction. Let me give you an example of this, because this is our main correspondence between polynomials and tensors, and from then on we will only be concerned with tensors and how to construct these symmetric tensors. So once we've settled this projection here, we can move on. So example, so we take, say, x is our vector 0, 1, and y is our vector y, x is 1, 0, y is 0, 1, basis of C2 star. So those are just in C2, but this dual space, so as row vectors. Just C2, but as row vectors. And now our f should be x squared y. That's our polynomial. And let h be the column vector 2, 3. What happens when we evaluate? So if you evaluate x squared y at 2, 3, that's 12, right? This other interpretation as a symmetric tensor is the same thing. You can write it as 1 over 3, 12 plus 12 plus 12. And why is that? So why do I do this? Because I want to show you that this is actually the same thing. So this tensor is x tensor y plus x tensor y tensor x plus y tensor x. So that's the symmetric tensor, x squared y. And we contract this one with 2, 3 to the third power here. Yes. So this is the same thing as just saying, well, this is x squared y contracted with 2, 3 to the third power. So this is how I want to make this. This is how I want to think of polynomials. I just want to think of these polynomials as these symmetric tensors here. Okay, and then I can evaluate by just evaluation is a contraction of tensors with a power, and this will be important. So evaluation is always a contraction with a power. Yeah.
Kind of like f was in your thing, f was a tensor. You wanted to show how from this tensor you get a polynomial.
Yeah, I mean, yes. It's now called f again. So
well, in your example below, you started with f.
Oh, this is we start with a polynomial, and well, I mean, this is a tensor also. I mean, this is.
Yeah, but that's exactly the correspondence.
Well, I want to show that if I write the correspondence from this one is the following tensor. This is if you take, okay. This is the tensor. This is the symmetric tensor corresponding to it. And I want to show that evaluating it is the same as the tensor contraction. So the correspondence is this one. So the correspondence is this one. You write it out as just as the symmetric tensor, and what there is to prove is actually that evaluation is nothing else than the tensor contraction, which basically follows from the definition of what the evaluation is. So you look carefully at what is actually polynomial evaluation, and then you see that this is actually the same thing. So, yeah. And you can actually even construct f and all its monomials if you want to actually do that. Then you can also do that if you want to do that. Okay, so the correspondence is just, this is written as x times y is a symmetric tensor, is this tensor here. That's the example, and hopefully should be clear from that example how to do this correspondence. And there's a formal correspondence which is called polarization and restitution, and it's this one. And the main point is that we can always do this one. This is our this is evaluation of a polynomial at a point. Okay, and there's a note. We have that so we get this projection of tensors. So say capital P is the projection from our tensors to symmetric tensors. Then, and written also on the right, written from the right. From the right is always, because this is functions, so I write it from the right. So then we have then this evaluation. So if you have your f and you project it, say f is, so you take your f, you project it, and then you contract it with some tensor power. And this is the same as just contracting f. And well, that's clear, but even, and that's the point, even if f itself was not already symmetric, but only some tensor. So you can write down polynomials now much easier, because you don't have to actually take care of the fact that your vector that you write down is a symmetric tensor. You can do this with any tensor.
So is the reason for that H is symmetric?
Yes, the reason. Oh yeah, the reason for this equality. Let me just quickly state this. The reason is that you can put brackets here, and since H is already symmetric, this projection basically does nothing, and you're done here. So you can always do that, even if your f is just some normal tensor. And I will construct these kind of tensors. Okay? And you can interpret them as polynomials since you can evaluate them. It's already defined. And we will have polynomials.
It's worth remarking that, although this looks like a silly trick, you were able to evaluate polynomials that other people could not come close to evaluating. One,
Okay.
that,
I mean, this
Although,
really
in
helps.
fact, that's what we do when we evaluate polynomials in a sense. You just pick one of the tensors and use that to evaluate it. But when you're doing it
Well-
by monomials, that's what you do.
Yes, when you do
Yeah, we already do
monomials. Yes, so when you do it with monomials, you do it like this, without the p.
yeah, but if
I understand.
representation theory hands you the
I
tensor,
understand.
it's not handed in monomials.
It's not. I mean, we will come to results later. I mean,
I know, but it's good to foreshadow.
Okay, it's okay. It's
Yeah.
very useful to see these things like that.
Monomials is
It's like
trivial.
really, really
Um,
amazing.
It saves a lot of computational time if you use like this. So reminder, the main things we are interested in are these, so that n, and this is the padded permanent. Those are the ones that we are actually interested in, and those are in some w, and w is actually the symmetric power of Cn squared. So that's what we're actually interested in, and this was defined as the invariant space, right? It was defined as this. We just defined it as the invariant space, well, over Sn in this case. So actually, so our W has a more complicated structure than it was actually as it would seem. So actually, what we are interested in is we are interested in these ones. So you have a sim d of sim n, and then you have a Cn squared star, and this one is. Let us have a look at what this one is. It's a bit of animation. So this is the d nth tensor power of Cn squared dual. And now, well, what should you do? What do you do? I mean, this is basically raising this space here to the d tensor power and taking its invariance, right? Because how you get the symmetric power, you raise it to the tensor power and take its invariance. So you take this space here, raise it to the power, and take its invariance. So you have this space. You raise it to the power, so that means you get these Sn cross Sn cross and so on, cross Sn invariance. And then you take the invariance again. So this looks complicated. And the nice thing is that we actually know already a lot about these things here, but we don't know a lot about the SD invariance. This is related to the tableau homework, where you actually knew a lot about the semi-standard tableaus, but then you had to take invariance and was not completely clear what was going on. This will be exactly this. Okay, but let me try to do actually this connection. So, so our W is some, or for a moment, let be, well, no, that's fine. We don't have to have that. We just take some space W. We want to know now what is the GL representation of it. So we have an action of on our tensor space by a GL as well. So we go to the capital D. So capital D will basically be D times n. This will basically be our main example. So you want to act on it with some G, and G is some element from GLW, say W. And well, this is just a right action, and we all know how this is defined. It's just the normal action that you would have. So it's GV1, then the GV2, and so on. There's a GVD. Okay, and we see immediately that both actions actually commute. So because this is only doing, so one is rearranging the tensor factors, but one is completely doing the same on each factor. So so those commute, which is nice. And now what is the highest weight vector? And those are actually the ones that we are interested in. So we will construct these.
Sorry.
Yes, sure.
Should G to be on the left?
Yeah, that should be a left action.
Does it have to be a left action? I can do a right action like this maybe. That's better. Let's do that. It doesn't matter. We will not be so much concerned I mean, it just gives upper and lower. It would be fine. I mean, okay.
Christian?
Yes.
Since this invitation is somewhat hard for me to parse, can you just like kind of tell me where the lecture is going so I can like try to focus on what's important for me?
Oh, yeah, the lecture is going to we are now constructing highest rate vectors, which are the inside tensor, inside this space here. And highest rate vectors will be the ones that we actually then take the project to the invariant spaces. So those will be polynomials, and for those we can see how to evaluate those. The highest rate vectors have the important property that they actually characterize the representation theory of the whole vector space here.
So today you'll actually be constructing these things and evaluating
Yes.
them somehow?
They will be actually contracted at the end. I mean, I mean, the point is to actually contract them at the end.
Okay.
Yes. And nice results actually. So we can actually express some results of some papers actually in that language and just contract them and see what happens and so those are not difficult if you just see what happens when you
So
construct.
just taking it a step further back,
Yes.
you're looking for useful equations in this gigantic space of polynomials on polynomials, right? So representation theory splits this up into small pieces, and he's saying you only have to check one vector in each of these subspaces, and then he's going to give you a recipe for how to check that vector without even explicitly writing it.
Yeah, we never write
Because
it.
if you write it, it'd be just gigantic.
And evaluating it where?
Well, I mean, for different problems, evaluating at different points. If you want to just check non-zeroness, you pick specific points that help you to evaluate it. You can pick generic points. You can also, of course, in this case, you would want to evaluate it actually at the determinant and at the
No, for
dependent
example,
variable.
in the permanent versus determinant problem, you take some highest weight vector.
Yes, we evaluate
the
the
ideal of
determinant.
the determinant, and you want to check whether it vanishes or not at the permanent. What does that correspond to?
Yes, you want to contract it with a tensor power of the determinant tensor. Take the permanent tensor. You take the permanent tensor, you contract it, and then you want to check if it's non-zero.
Much faster, meaning.
Hmm?
And you are saying that you don't do it in an obvious way, but in some other way which makes it fast, right?
It's faster apparently, but we haven't analyzed its complexity. It also gives you theoretical results though, and it's very fast also.
Yeah,
Okay.
it's much better than what other
I
people
mean,
have done.
complexity
Yes, okay.
theory.
But complexity theoretically,
No,
I
that-
understand. I mean, we did not study the complexity of the
But it's
algorithm.
much better, that's all.
It just gives you, for the small examples, it's good. And it gives, actually, so for example, there's a paper by Kadish and Landsberg, and the result, you can immediately get it from this. If you see it as a contraction, then it is an application of the pigeonhole principle, and you see that, and we get basically the result of that paper. And you can see it like that, which is really good, because the result itself is really, really good and tells us a lot about the partitions, right? So this is very helpful. So highest rate vectors, and we know that highest rate vectors are sufficient as obstructions. So we want to construct exactly those vectors. Those are the ones that, if you want to study things with representation theory, it should be highest rate vectors. So I want to define now what that is, because those are the important vectors that we want to look at. So there is the UN sitting inside of GLN, and let this be just the group of upper triangular matrices, ones on the main diagonal. Those are the maximal unipotent group. And then there's a torus sitting inside, which is this one, just having, this is the torus, right, like the diagonal matrices. So now, first let's define what a weight vector is. So you have F in some representation. Say V star is a representation, and then a weight vector satisfies just that it's scaled by the action. It says that for all, and now you have T1, T2, up to Tn in the torus, that your F, if you act on it with a torus, it is just scaled. So this F is actually well, I need more space for what it is actually. It is the following. It's those are just scalars, right? Just complex numbers. And your f, if you act on it with a diagonal matrix, then it gets scaled. And these are the scaling factors that it picks up. That's a weight vector of weight lambda. And lambda is actually, well, those are just, if this is a polynomial representation, then those are natural numbers. So it's a pair of, it's just a set of natural numbers, and those give us our scaling. That's a weight vector. And now a highest weight vector.
Inverses.
If it's a polynomial representation, what you need inverses, you say here?
Because your action is like right there.
Oh, now the action is this way. Well, then you can put inverses here. You say it should be inverses? I mean, you can also replace it with z's here. So it's up to a sign this is correct, okay? Up to a sign this is certainly correct. So weight vector f in this representation that satisfies another constraint. It satisfies for all group elements in the unitary group, a unipotent group. It satisfies that actually if you take your tensor and you act on it with these upper triangular matrices, you get your tensor back. And if you have that, it is called a highest weight vector. And this looks a bit, well, this comes from representation theory, and you can prove that this basically defines your representations. So every irreducible G in representation has exactly a single highest weight vector. So if you're interested in the representations that occur, you look at the highest weight vectors, because the dimension of the highest weight vector space is exactly how often your irreducible occurs in your decomposition. Okay, so those are highest weight vectors. So HWV of lambda of some representation, it denotes the subspace of highest weight vectors of weight lambda. So it turns out that lambda is actually always a partition. Let me give you an example, an important one that we will need, of a highest weight vector in our space. Because this is a bit complicated definition, of course. Let me give you an example. So the example is D sub I, which stands for determinant. And we want to have the following vector. It's E1, wedge E2, wedge E3, up to EI. And this should be a vector. And as always, this is correct up to left and right action. If I did it wrong, then I apologize. So this is a vector, and this is a highest weight vector. So this is a highest weight vector of weight. Well, its weight is easy to determine because you act on it with a torus element, which is diagonal matrices, and the E1 just scales to the power of 1. There's only one E1, there's only one E2, so this is all just by the. So lambda 1 is 1, lambda 2 is 1. So the weight is actually 1, 1, 1, and so on, 1, and then zeros. And this is I times. And this is a highest weight vector. It's a building block of a highest weight vector in your tensor space.
Don't you have to prove it? Don't you have to prove it that it's invariant under...
Yes, you can do that. So, yes, of course, you have to prove everything. So, it works as follows. If you have, say you have an upper triangular matrix, so say you have some entry here, then basically means that you change some E3, for example, to E3 plus E2. And then you expand this thing, and you get an E2 wedge E2, which cancels. So this one, and that's basically generalized. Right? So this is a highest weight vector. Yes, well that's, of course, yeah, so we proved that. And it has a computational aspect. So when you contract this tensor, so this is why it's called a determinant. If you take this and contract it, so you have, sorry, this is a contraction symbol here. So you take a di and you contract it with some tensor, y1, y2, up to some yi. Then what is that? So and the yj, say, let's take them from c to the n. So what is that? This is, if you contract this, it gives you a determinant of an I by I matrix, and this is now the crucial point is, this is, you take your vectors y1 up to yi, and basically just write them in a matrix, so they will have columns, I columns, but they still have n rows. When you only take the upper I rows, gives you a square matrix, and you take its determinant. This is exactly what this contraction is. Well, this is a determinant, because if you contract with such a tensor, you get a determinant. So this is a determinant. Yes, so this is the determinant of the I times I matrix, where the jth column is the first I entries of yj. Okay, so we get a square matrix. And then you can use this as a building block for more advanced highest weight vectors. And we basically get every highest weight vector in this way. So this is a construction that is, in a sense, a canonical construction. We have to, of course, we chose the basis, but I mean, we can show that this construction is basically the only construction there is for highest weight vectors. What you can do is, so the important example, so let lambda be a partition, and now with capital D boxes and column length, the column length should be theta 1 up to theta j maybe, then the vector, and I want to call it lambda, it's lambda hat, is defined as the tensor product of these determinants here. So it's over, you take every column and you contract, and you tensor them up. So the vector, this vector is a highest weight vector of weight lambda. And the proof is the same as the proof of this highest weight vector. Because you let the torus act, and you know how the torus acts on the single factors, so that gives you the correct weight. And then the UN invariance you also get because all the single factors are UN invariant. So this is clear that this one is also a highest weight vector and has the correct weight. So, okay, so since the actions commute, the actions of the general linear group here and the symmetric group, those commute. So whenever something is a highest weight vector, see this was only defined, of course, using notions of GLN. So you can now also apply permutations from the symmetric group on D letters, and you still get a highest weight vector. So this is because of the actions commute.
This is not corresponds to reducible representation, right?
It will correspond to irreducible representations. Oh, let me say that actually. Let me say that maybe. I can tell you that also, of course. That's so every irreducible GLN representation contains, up to scale, of course, exactly one highest weight vector. Okay, and so if its weight is lambda, we call it the representation lambda in these curly brackets. And yeah, so in particular, we see that, and this of course all requires proof, of course. In particular, we see that the highest weight vector space with weight lambda of lambda is one-dimensional. And we see that the highest weight vector space of mu of lambda is zero-dimensional, right? So that's zero. Because it has only a single one, and if the weight is correct, this only matches. So you get more highest weight vectors when just applying elements of the symmetric group to this highest weight vector. So you get more. And we want to have more. We want to have all the highest weight vectors that we can get. So that's what you do. So the X's commute. So what we have is not only lambda hat is the highest weight vector, but also lambda hat, if you apply pi, is the highest weight vector. And well, the next section tells you that these are actually all the highest weight vectors. There are no more highest weight vectors. And this is called Schur wide duality. Tells you that this is actually an exhaustive list of highest weight vectors if you take into account linear combinations of them. Well, linear combinations is of course allowed. So the theorem is the following. And this is the most important theorem, which actually draws the connection between the general linear group and the symmetric group in these cases. So it's this one, the d tensor power of Cn star. How does it decompose? It decomposes over lambda into tensor products, which are the irreducible GR representations, tensor the irreducible Sn representations. This is how it decomposes. And those lambda, those are, well, lambda is over all partitions. With capital D boxes and at most n rows. Okay, and that's a very interesting correspondence where we can make it very precise. We can make it much more precise as, so we already see from the last lecture, we know exactly how this space looks like. And we remember this is the reducible as D representations here. And we know that the basis here is given by standard tableaus. So we can make this very explicit here. So we had a highest weight vector here, which was lambda hat. How does it correspond to some highest weight vector here? And it works as follows. So the highest weight vector, lambda hat, on the left-hand side corresponds to, on the right-hand side, this is the following. So you first get this, there's only one highest weight vector here, so that's clear, so that should be highest weight vector lambda of lambda. But now you have some tableau here, and let me just do this in one example. So it's called the column standard tableau. So let's just do some example here, otherwise notation gets messy. And this is column standard. Column standard. This will be the highest vector that corresponds to the, I mean, you know how to fill it, right? You just fill it column by column. Get a standard tableau, and that's this one. Yeah. So, in particular, if we have this strong correspondence here, the Schur wide duality, we can now have a look at the highest weight vector space here in this space, of course. And this is what, because we are interested in highest weight vectors here, let's just do that. So, let me just do it here. So we look at the highest weight vector space in that space. So consider some partition mu. I want to look at the highest weight vector space. Well, there, if you take the highest vector space of this large sum, there's not much that actually survives. Because there's only actually one summand that survives. So highest vectors.
Can you just be more precise regarding to which representation you are, because you have two groups here?
Oh yeah, but highest vectors only is only for GL representations.
Ah, okay.
The SM they don't have that. So okay, highest vectors of this space. Well, what is it? It's the highest vector space of the whole sum. So you can draw this into the sum. And we know already how this looks like. This is exactly only this one-dimensional thing here. So all the, I mean, this is zero-dimensional very, very often, but in one case, where it is one-dimensional. It's this one. So highest vectors here correspond exactly to, well, this is one-dimensional, so this is exactly the SD representation. So as SD representations, these two spaces are the same. Those are isomorphic SD representations. So all the representation theory is actually only going on in these tableaus. So you can actually do all this thing with, well, without thinking of polynomials, you can do everything with tableaus. Okay, so this is of course super very, very nice. So we now so these d times n. So let's get started and say d is d times n, and observe that actually the d tensor power of Cn star is the d tensor power of the nth tensor power of Cn star, or just divide it into 2. And now we do these projections. So we project down here to the d tensor power of also to the symmetric power now. And now the first interesting thing happens, and it's related to your homework assignment. So well, we know that these are the standard tableaus. So a basis here of the highest weight vector space is given by standard tableaus. Let me make this more precise. Let me just write highest weight vector spaces here everywhere. This is the highest weight vector space. It projects, of course, to a highest weight vector space. So now, what happens is a basis here is given by standard tableaus. You project it down. Basis here is given by the semi-standard tableaus with rectangular content. And you see that by seeing, well, what happens here is that actually you have in your tableaus numbers 1 up to d times n. So what happens is you identify the first n numbers in your tableau, and they just become a 1. And then the second n numbers just become a 2. And the further numbers, they become a 3, and so on. So you have you have n numbers, so the numbers come in blocks of n. So this is basis given by standard tableaus. And the relations are exactly the Grassham-Plücker relations. They of course still stay the same, right? So this is standard tableaus. And now here's a basis given by semi-standard tableaus. With content. And it was n and n, right? And not only that, I mean, it's not only theoretical, it's very explicit. You can write down, you basically do these contractions.
Christian?
Yes.
You explained this to me once, and I think
I can do an example.
One example.
Yeah, sure. I will do an example of this, of how to project a standard tableau to a semi-standard tableau.
Listen.
Yeah.
One formula there. Second last formula on the whiteboard.
This?
Does it say C capital N star?
It says C to the n star.
It's not D capital D.
It's C to the n, and it's, I just put a star because I think of row vectors.
What is N?
C to the n is the C to the n is the is the just complex numbers raised to the nth power is the vector space.
But you had like, you defined this capital D there.
Oh yeah, that's capital D is, well, capital D is just D times n.
But different end.
It's a different end.
There's a little n and a big n.
This is a
The
capital
little n
N
is
here.
in degree, the big n is dimension.
Oh, you can think of, if you want to, you can think of this as n squared if you want to, because this is the number of variables we are interested in for the determinant. So if you want to, you can think of capital N as n squared. But if you can also enlarge it, it's just some big number. This is as large as you want it to make these statements too.
D.
If you have a D, it's fine. Yeah. Okay. I want to give an example of this projection. So yeah, if you have 1, 2, 3, 4, this projects to what? You take this block. These are the first numbers. Those are the second numbers. So this projects to this. Well, this was a S4, and this is now, if you project to the second power of sim 2, then this is this projection. And if you would have started with that tableau, this would go to 1, 1, 2, 2, which we learned last time is actually 0. So that one vanishes under this projection. This one does not vanish, it stays here, it's the basis vector. Okay, so that works. And now,
I see. So the of the ones that are non-zero, they're pre-images of the standardization of them.
the pre-image is a standard.
It's the standardization. That's a.
I mean, if you start with a standard tableau,
Yeah.
if you have a standard.
No, but there's a standard way to go from a semi-standard tableau to a standard tableau called the standardization.
Okay.
I guess that's what it is.
Well, I guess I'm not familiar with that concept. Just you put in, basically you have these blocks, you put in numbers 1 up to n, and then takes the next block, put in numbers n plus 1, and so on.
I mean, in combinatorics, you see a string of equivalent numbers. The ones further right are larger, and that breaks ties, and that gives you a standard tableau. That's called the standardization. I think
there's not much going on.
Yeah, there's not much
Okay,
going
so
on.
and there's no sophisticated, no jeu de deck, whatever. Just you can immediately write the numbers in. Nothing is happening. So of course the most important thing now is if we are at this point, we want to somehow evaluate these things, because now this is the most interesting thing. Is now we have these semi-standard tableaus somehow, and we know we don't have to take care of this symmetrization, right? We don't, because we know we saw in the beginning that it's superfluous to take care of that symmetrization. We can just contract, right? We don't have to project it here. So basically we are done here. We just want to know how to, if we write down a semi-standard tableau, how to do this contraction now. So what is this? And it can be interpreted combinatorially. The semi-standard tableau actually now defines a polynomial. You write it down, it's the polynomial. After projection, of course, but you don't have to project. So now, well, evaluating is now this contraction. You have your lambda hat, you have your pi acting on it, which is basically pi is giving your semi-standard tableau, and you want to somehow contract with some tensor y. You raise it to the dth power, and y is an element of sim n c capital N.
So I'm just getting confused. So in the case of permanent versus determinant.
Yes, your y is determinant, for example.
Y
Y is your determinant here.
it is sitting where now?
It is sitting inside this space here. It is sitting inside this space.
I thought it would be sim d then.
It's sim n to the cn squared, which is
times sim d, right? It will be Blachy's operator, isn't it?
this is yes, but this is not the sim yet. I mean, because we don't have to. You could do that. You could project even further,
Yeah.
and that would be sim d.
But isn't that where determinant is, that thing is?
Well, the
sitting?
determinant itself is of course.
Yeah, no,
But the highest value is there, yes. But we don't have to actually do that because the contraction takes care of that. So if you contract this tensor with that tensor, you can throw out actually this symmetrization in between. But yes, you're right. The highest value itself is the image under that projection.
And you are not going to, your point is you are not going to do evaluation there, is it?
I'm contracting this tensor. I'm contracting the tensor here
Yeah.
with that tensor over there, which automatically projects the tensor. Because you can, if you have this, you can squeeze in between a projection operator if you want to. And then this is your highest rate vector now. But since this is already symmetric, this projection operator actually does nothing. So you can strike it out. You don't have to have the projection. So you can actually work with the ones that are not projected. This is actually very, very helpful. I mean, because we know what we can write on all semi-standard tableaus quite easily.
Only problem is that if you do the symmetrization, you won't have a basis anymore.
Yeah, you don't have a basis anymore. This is a basis. Yeah, it gets really complicated. We know that from last lecture. It gets really complicated and you don't know actually what's going on. Because the dimension of that space here that you get when you go to sim here is the Plathism coefficient. So you don't know much, right? We know from last lecture that's a big problem.
So the point is you don't need to know the decomposition.
Yeah, you don't need to know the
I'm
decomposition.
just trying to understand.
Yes, you don't need to know the decomposition.
The
That's
valuation
exactly
projects for you, I guess, that's the point. The valuation does the projection
Yes.
without you having to do
Yes, evaluation does the projection for you, yes.
This is free lunch.
it. It is.
It's free lunch. It's a
The economists
defactorial.
don't like this.
It's a defactorial free lunch that you get. Yes. So, okay. So now what you want to do is now evaluate this thing, and there is a pictorial interpretation actually of that. So what you want to do is let me give you a pictorial way of actually doing this evaluation. It's a tensor contraction, and if you go through the definitions of lambda hat and pi, then you get the following combinatorial interpretation of what actually happens when you have such a tableau and you want to evaluate it. So this is your tableau, say this is your tableau. Then you evaluate it at a times b, say a times b, yes, that's as symmetric tensor. And well, what happens is, I mean the number of variables is exactly the block size, right? And what happens is you put in your tableau your vector AB in each block. So that's AB here, that's AB here, that's AB here. Take this, and then you sum over it, and you have to put it in all kinds of different ways, because this gets quite messy. If you expand this, it gets really messy, and then you have a lot of summons. But that's what you get. So you put your into your blocks, you put all your things, and it will get messy. So there will be more and more, but in every block, right? In every block, you have exactly a B and an A. That's the requirement. Because BA is where you want to evaluate. And then, well, what are those numbers? Those numbers are now these the contraction of these DIs here, which are determinants. So each of these summons is exactly one determinant. So it's the determinant of AB here, and that's the determinant of BB, which is, so this one has actually,
0.
let me write, yeah, this is 0. So that's determinant of some A column, well, which has only 2 entries, sorry. So that's AB times determinant BB, which is 0, times the first entry of A, times the first entry of A. And that one here is determinant, and it has columns BB, has times the AB, times A1, right? And so on, so you sum over those. Yep.
Can I ask what? So I just.
Sure.
Permanent.
Yeah, sure.
So instead of evaluating that projected thing as permanent, you are going to evaluate the unprojected thing at what?
Well, at the permanent.
But at the raised to a power.
Raised to a power, so you raise it to a power, so you make it symmetric. So this one is actually symmetric. If you take the permanent and raise it to the d power, it's symmetric under SD.
Yeah.
So you raise it, it is symmetric already.
Yeah.
So if you contract a non-symmetric tensor and a symmetric tensor, it's the same as first symmetrizing the tensor and then contracting.
Okay.
So you get something like this, and which is very. I mean, I will show you now how this actually works in practice.
Yeah.
If you yes,
That would be very.
yeah, I can show you. So there is a theorem. This is Kadisch-Landsberg. And of course the language is different there. And this is my interpretation of it. So you want to contract now, say you have a tableau. If lambda has a first row shorter than n minus m times d, then all highest weight vectors of weight lambda vanish on, well, let me call it z to the n minus m times some h, where h is in sim m c n, maybe it doesn't matter.
So does this result fall out of your scheme?
Yeah, this follows now.
Okay, good. So now I see.
See, this follows now, because what you do is you write down your tableau. Say you have a short first row, and then you have some other stuff here. And now what happens is, if you evaluate at this h, at this, that's important. So this tensor has the important property that if you expand it if you write it as a tensor, then it has n minus m factors that are z, right? That are exactly z. Right? It's n minus m factors. And now, well, whatever your block arrangement here is, doesn't really matter how you arrange your blocks here. Every block, so in the evaluation, every block will receive, well, it receives n minus m entries z. So now what happens is the following. So in total, this whole each summand has d times n minus m entries z. So in total, every summand, and summand, I mean something like this. That's a summand here. And it has a's and b's. And we've seen already something like this happens quite well. If you have a b and b paired, the summand vanishes. So in total, every summand gets d times n minus m entries z. Right? So now, what happens if your tableau is too short? Then what happens is that at some point, by the pigeonhole principle, we will get something like a z and another z on top of each other. Right?
It's less than n.
Yeah.
What? dn minus m, if it's shorter than d times n minus m. So in total, every summand gets d times n minus m entries z. So if this one is shorter than d times n minus m, and right sometimes d, then there has to be, by the pigeonhole principle, some pairing z and z, right? It's just, you have,
One column has two.
one column has two z's. So
What is z? What is z? That
z is the padding variable.
That.
It's the padding variable, yes. So the pigeonhole principle says, well, basically says all columns vanish, all summands vanish, which is, of course, the strongest thing that could happen to make something zero is all the summands. There's no cancellation, it's just all summands vanish. Right? So, hence the evaluation here vanishes. It's the proof of this theorem.
What is it?
Oh, a block is a collection here of ones. That's a block. And this one is a block. And that one is the block here. In your semi-standard tableau, you have ones several times and twos several times. And each collection of ones is a block. The collection of twos is a block. The collection of threes is a block. And in every block, you put in your polynomial. And it just happens that you have too many z's. So you always have a pairing like that. So that's basically follows from pigeonhole principle and this viewpoint, which is, and the theorem is rather strong, I must say, because it gives you a huge reduction of your search space for obstructions in geometric complexity theory. But it basically says that your partitions almost only consist of one long first row.
Sorry.
Yeah, sure.
I don't get it. So in every evaluation,
In the evaluation. In the evaluation, which means evaluation, I just did it by example. You evaluate by taking blocks and putting your polynomial in every order inside the blocks. So that was the first block, was 1, 1. And you put AB in there, but you also put BA in there. And every rearrangement gives you a summand. And you sum over all these. You put in your polynomial into the blocks. So this is the polynomial, it's AB
How
here.
many boxes is left? How many boxes is left?
D times N.
D times n boxes. D times, this is, so this one is D times n boxes. And has, the content is n, like we had always. It's n1s, n2s, n3s, it's n. And this one is a tensor, it's a tensor of order n. So you can put it exactly into a block. And you can put it into the next block. It has n entries 1, you put it into where the 1s sit. And you put it where the 2s in every reordering.
That's neat.
Hmm?
That's neat.
Yes, I very much like this
Now
theorem.
I understand it.
I like this theorem, yeah. So you can get more. So I have a reinterpretation of a proof that we did, which says, well, yes, 5 minutes is fine for this, I think. So it's called even partitions and plathisms, and it says.
But the point now is that you only need to look at the first row bigger than
The point, of course, I mean, why is it interesting, this theorem, is, of course, the reason is that the things that can actually only be obstructions in geometric complexity theory, they are not allowed to vanish on these things, because they are not allowed to vanish on the permanent. So you cannot have short first rows, because they will all vanish if you evaluate at the permanent. Your functions are supposed to vanish on the determinant, but not on the permanent. So if the row is too short, it's not possible. Okay, so I just want to quickly remark that you can, if you study this, it doesn't matter, you can do this, yeah. If say we have this, n is even, and lambda has only even parts, so even rows. So even number of boxes is even. Then the plathism coefficient is positive. Why is that? By evaluation.
So maybe you should mention the history of this question.
But you know it much better, of course. This one. This
Yes.
is a conjecture. Oh yeah, that is a.
You certainly know that better than me.
Oh yeah, this is a conjecture by Weintraub 20 years ago, and there was a partial resolution of this question by Manivet, and we solved it with Matthias and Peter, and we got some insights on this plathism coefficient for that. So it has grown also to pretty deep understanding of why this is actually true and how to prove positivity of plathism coefficients. Okay, so it was.
You should write your co-author's name on the board.
Of
You don't have to
course.
write your own.
That's not.
Doesn't like his own.
That's okay. I mean, that's his choice.
Sorry. These are my co-authors, and Constantin is basically the guy who taught me all these how to look at tensors the right way, so that we can actually was actually also the driving force in getting this proof done. So what we can do is now see if lambda is actually even. If lambda is even, then you can find a tuple which is really neat. So you put in each you pair your columns into sizes of 2. So they come into in these flavors, right? Because it's even, you can do that, and so on, something like that. You can. These are 1s and 2s. So what you write down is you copy basically whatever is written here to the next column. So you get some fitting that looks like that. And now what you do is you evaluate at a power sum. And it gives you basically the right thing. It gives you, so at the power sum, but the point is, so you raise a1 to the n plus a2 to the n plus and so on, plus say a d to the n. But the main point is here, the aij, the ai, say those are real numbers now. If you only take real numbers, say what does the evaluation do? You plug in you plug into your blocks that are somehow distributed here, but not arbitrarily, but it come in pairs. You plug in the A1s here. I mean, you have to reorder, but reordering is not possible because it's a power sum. It's already symmetric. There's no reordering. You replace the A1s by the ones by A1s or by A2s. Doesn't really matter actually. So you place the numbers by these values, and then you take the product of the determinants. But what happens when you take the product of the determinants here is you pick up the same determinant always twice. So you pick up the determinant and the determinant of the same matrix again. So you get a square of a determinant of a matrix with only real entries, which is then positive. And you pick up the same thing here, so the same thing here. So you get a product of positive numbers. And you sum over all those, and you sum up positive numbers only, and this is non-zero. So you show by evaluation at the power sum, you show that if you evaluate this polynomial here at the power sum, you get a non-zero value. In particular, this polynomial isn't zero, so the Platheism coefficient is also not zero.
This your evaluation scheme, does it give some heuristic idea of how often these Platheism coefficients vanish, for example? I mean, on the basis of this pigeonhole thing, I mean, does it give some...
On the basis of the pigeonhole thing, yeah, I don't have a... Still don't have a
But
good
you must have done
understanding.
experimental thing, right?
Well, yeah, I mean, we are doing experiments, of course, with these
And
things.
what do you see?
The Platheism coefficient, when there's a zero Kronecker coefficient, which we want to have, then it just happens often that also the Platheism coefficient is also zero. But sometimes it does not, and we have a list, there's a compiled list, it's pretty long, it's several hundred, that where actually we get a positive one here and vanishing Kronecker coefficient. But still the question is open on how to determine if this coefficient is positive or not, and we even lack sufficient criteria. Something like, I mean, this is a nice criterion for proving a coefficient is actually positive, but the corresponding Kronecker coefficients that are interesting in geometric complexity theory, they always vanish.
Yeah.
So that's all my calculations I did is that this criterion is not quite enough for positive. I mean, this does not give the right partitions. So we have to refine, that's actually also the project, refine these approaches to get more sophisticated, sufficient criteria for positive Platheism coefficients. Right? This is important to get these criteria, where you can just say, well, the shape is like this, so it's a positive Platheism coefficient. Because deciding positivity might be too hard, but in all the cases that we actually calculated, replace the computer proof by some insight that we have. From the shape, it should somehow be clear that this coefficient is positive. And maybe not in all cases, but maybe in just enough cases, so that we somehow, at least in a large part, can actually have a non-computer proof of what we have already computed. That would be nice if we could find something like that. I think that's it.
We have still have time for questions, comments? I have a quick comment.
Sure.
You actually proved something stronger there because you're proving that this module occurs in the D-C-camp variety of the Veronese at D.
Yes.
Or, which is meaningful if D is not enormous.
Oh, well, that's even better.
Yeah.
Yeah. That's true. Yes. I wasn't thinking of that when we did that. Yeah, but that's, yes, you're
Now
right.
you can.
Yes, that's right.
Maybe
Yeah.
the comment you made it's at the end regarding Kronecker coefficients. So you said for those lambda,
Yes.
where we now know the Platheism coefficient is positive.
Yes, by this rule.
Yes, what did you say about the Kronecker?
The Kronecker coefficient is, so if you have lambda and two rectangles, in the case for the 3 times 3 determinant, so if you have 3 times d rectangle, in these cases, it always happens that the Kronecker coefficient is also positive in these cases, which is related to the paper that we had with the stretching property. So the stretching factor in these cases seems to be 2. In other cases, I know it's not 2, but in the cases of relevance, it seems to be 2, which is unfortunate.
So if I understand correctly what's going on in terms of writing down polynomials via representation theory, I mean, in this case, due to this evaluation, you're getting a summation over tableaus. Is that?
Yes, it's basically over tableaus, so you can interpret this as a summation over tableaus. So the relations here, or the tableau relations, still hold even if you plug in these B's and A's. And you can explicitly evaluate it if you go to the determinants here of these vectors. But you can also just let it as variables and say replace the A's by 1s and the B's by 2s and just do the calculation in the space of tableaus. That also works. Because the relations are the same. So the relations of these determinants here and the Russell-Picker relations, those are exactly the same. So you can do all this calculation, and this is then symbolically on just the space of tableaus. But you can go to and do this numerically if you want, or some finite field if you want to here, because it's a bit easier just doing this calculation. Then what you would have to do is you have to express it in the basis of semi-standard tableaus. You have to straighten the tableau, which is sometimes more just takes more time. Actually, maybe a lot more time than just calculating this product of determinants here over some small finite field. So. It just depends on what you want to do. If you want to prove that something vanishes, then of course it's important that you use the tableau approach. If you just want to show non-vanishing on some point, you can just replace it by this calculation over a finite field, and it's just really fast.
Okay, well, speaking a little bit more theoretically, okay, so if you wanted to show that this summation is 0,
yes.
Like one technique is to show all of the terms are 0. Which
Well, yeah, that's
is
one technique. Yeah.
Restricted way.
I think that's almost the only way that people have used so far. Oh no, sometimes you have cancellations, very easy cancellations, where you have a lot of summits and you see a pairing, and then you have positive and negative summit, and they all pair up,
yeah,
and then it vanishes. Well, that's also a very simple way of seeing a vanishing. And we are still working on refining these methods. It just gets more and more complicated once you take into account more of the symmetries and ways that things can actually cancel. It gets really complicated.
I think I've asked you this before, but so I mean, as written, it seems like this is in BNP, but I think is this degree issue also still there? I mean, it seems like this is okay, right?
I think this is it seems okay, yes, because it's an exponential sum over product of determinants.
Yeah,
It should be okay. Should be okay.
So how large can you go in the calculation, like in determinant versus permanent? How the size of determinant can
we
you go?
cannot. We did not find anything that is satisfying for the 4 times 4 determinant, and even for the 3 times 3. What you can show is that if you have some, say, some h in sim 3, C7, and if this is generic, then you have h is not inside G9 that 3 or closure by finding an obstruction. But this is the only thing that you can. We cannot go to that 4. It's not working, and even this is not. I mean, that 3 you cannot really compare it to the permanent, right? You cannot really do that. So that 4 we are still lacking information on that 4.
I mean, you can't evaluate that, go that far.
I mean, it works, but there are so many things that you would have to test if those are actually obstructions. You can do things like that also for that 4. It's just, it gets hard. And also, but also evaluating at the determinant, you don't want to do that because that also gets out of hand quite quickly. That even that 3 is in degree, what degree did we have? Degree 12 or something? We tried to evaluate some polynomial at the determinant, which was important for the, so there's this polynomial which defines the difference between the old and the old closure. We wanted to check if that's non-zero, and we didn't manage to evaluate it, but we have some ideas on how to use the special structure and to make it faster. So that 3 should be fine, but that 4 is completely, at the moment, is out of reach to actually do these calculations. But do we have
If you do it naively for det 3, you get up to degree 9.
naively up to degree 9?
When you do this,
Yes.
what you presented.
Yes.
On a personal computer, degree 9.
Yes, we run calculations degree 9, which is not sufficient, of course. But you don't have to, of course, evaluate at the permanent. You can also say, or make it easier and project it first to some smaller thing.
No, but how large do you go in the coordinate ring? How high degrees do you have to go?
9, did you say, right?
9.
9. But the first things that we find using Kronecker coefficients is the first things appear in degree 10. So we cannot actually
10.
degree 10 is the first things that we
For
find
degree
using
10.
chronic. Using
For indeterminate 3.
yes, determinant 3 is if you compare chronic and Plathysm coefficients,
Yeah,
you
you
look for
have-
obstructions, it's degree 10 the first that occurs.
Should be quadratic approximately, right?
From one example, I have no idea.
That's right.
I know it.
Gosh, the one example.
No, not on this basis.
No, I don't. I have no idea. I have no idea how it is. I mean, we have to evaluate this. I mean, we have to study these things. I don't know. I really don't know. So, well, we cannot go very far with that. But I mean, nevertheless, you can derive theoretical results quite quickly with these, right? So this is not. These are not very complicated proofs if you use this approach. So we can actually get insights. And yeah, I'm really looking in. So we should definitely be able to get more criteria like these and get more information about positivity of Plathysm coefficient, because this does not seem to be the hard problem. The hard problem is that you get a sufficient criteria that tells you this Kronecker coefficient is 0. We don't have that. For the Plathysm coefficient, we can derive all kinds of things and look at the structure of these tableaus and then somehow don't have to go over the whole expansion here, but reduce it significantly and prove that something is actually positive. That's much easier. And also you can choose points where you want to evaluate and things like that. But the Kronecker coefficient vanishing is hard to prove. A way of proving that a Kronecker coefficient is 0, I don't know of any way of proving that at the moment. In our relevant range, right? Not some trivial inequalities. And that would be a challenge.
Other questions? Well, let's thank Christian again. A lot of people